All right, so next exercise 8.2. And so now the big difference in 8.2 compared to 8.1. So 8.2, you're asked to construct a TXY phase diagram using Rayo's law. And so what that means is pressure. Pressure is constant. And so we're again going to set up a for loop where you have a vector of x values. You loop over those x values. And for each x, you solve for y and t. Okay, and so the big thing that's going to change here is t is not constant. So you just can't go ahead and pre-compute P1 and P1 set and P2 sat at the very beginning. And so you're going to have your call to your Antoine expression within your error function, right? In your error function, you're solving for t. So for each guess of t via fsolve, you're going to need to calculate P1 sat and P2 sat. Okay, so let's take a look at the code that I was sent. Okay, so let me just clear this up. This is, let me clear my variables and clear my screen. Okay, so that's we're just looking at 8.1. Okay, so now 8.2. Let's see what we have. Okay, so now this is 8.2. Okay, let me try and get my head off to the side. Okay, so similar to the last one. So now I just have Antoine and P as inputs. You have your reference temperature, reference x and y, so it's just the reference data as vectors. Yeah, so just already, so the issue is here, right? Antoine caller. Okay, so what are you doing in Antoine caller? You've solved for t, right? So that's going to be the issue. So what I'm actually going to do is, just so I can copy and paste, okay, I'm going to open up your code from 8.1, which we just worked on, okay, and so let me maximize this, okay, so I'm going to go to row 2, okay, so now I'm going to comment this out for now, okay, so you have your reference temperature and compositions are fine, okay, you have your x and y, your x vector, so you're going to loop over these x values. Bam. These are vectors in which we're going to collect our computed y's and t's. Beautiful. I'm going to loop over my x vector, and for each x, I'm going to solve for that particular case of x. Okay, good. All right, so how I'm going to update things is just already thinking about my anonymous function. Where things need to change is my x value for this iteration. That's going to definitely be an input. Okay, but t1 and t2, right? So what you're calculating is t1 sat and t2 sat for that p, right? And yeah, that should be your endpoints if we were to use that to debug your TXY diagram. But what we actually want is, let's pass your Antoine constants. So what we're going to have to do is you're trying to solve for y and t. And so what's going to happen is P1 sat and P2 sat are functions of t. So for each t, the value of P1 sat and P2 sat is going to be different. And so what I'm going to have to do within my error function is for that guess t, then solve for P1 sat and P2 sat. Okay, so what I'm going to do is I deleted T1 and T2, which you'd calculated there as inputs, and made it ANT. And then I'm going to come down to my Rayolt solver here. Okay, and I don't want this to be, I don't want t here, right? Okay, this is made ant my inputs. Okay, so when I unpack y, this is the vector containing the variables I'm trying to solve for. First element could be y. Second element can be t. Okay, that's fine. Okay, but now if I think about that, I also need p. So x1 ant, and I need p. Okay, so my pressure, which is fixed. So when I come down to my error function, it's going to be y1 times p, y2 times p. Okay, so hold on. And added p after ant. Added p after ant. This is going to be y1p, x1p. That one I need here isn't T1 and T2, but it's going to be P1 and P2. Okay, so what I do then is I'm going to go back to your code here. only because I know you did it here. Okay, I'm going to have P1 and P2. Okay, I'm going to calculate P1 and P2. And then I'm going to need your Antoine function from this code. Okay, where you convert the temperature from degree C to Kelvin. Okay, and let me delete this. Paste this. Okay, so now here. Okay, the units of temperature are really. Oh, call them ant. The units of temperature are really arbitrary, right? Because the only place the temperature comes in is in my Antoine expression. And so, I could create a TXY where my temperature is in degree C or Kelvin. Here we'll just make it Kelvin, right? But if I wanted to, I could just kind of made this temperature in degree C and created my TXY that way, only in that temperature only comes in directly in your Antoine equation. Okay, so what have we done now? So now my air function, I'm going to try and solve for y and t. Okay, then, it needs to be a little t. Okay, then, with y and t, I calculate y2, I calculate x2 from the specified value of x1. Then with that value of t, I go and I calculate p1 sat and p2 sat via my Antoine equation. Okay, so t is the same as knowing p1 sat and p2 sat via my Antoine equation. So I just copied and pasted that from your last code. Then my air functions we updated, right? And just to show you, this is essentially the same. So here's my air function, right? It's essentially the same as your last one, y1 times p minus x1 times p1 sat, right? They're exactly the same. The only thing we had to do here is p, which was a little case in this case, had to be added as an input because I'm solving for temperature. And once I know that temperature, right, I don't know P1 and P2, right, those aren't pre-computed. I have Antoine constants instead, which I use to calculate P1 sat and P2 sat for that T. Okay, cool. But otherwise, it's exactly the same. So, let me also go back. I need to minimize this so I can see my viewer. I think this was S6. I'm going to also go back and take your rail caller, and let's call this rail caller 2. Okay, and so I'm looking at rail 2. You need ant and p. Okay, so I'm going to keep. Keep this as my matrix of Antoine constants. Delete my reference values. Okay. Now I have P. And I could look in the problem statement, but I think I get it down here. P is again, same last problem. Look, 223. Come on. 223. Just looking at your notes, you had 233, right? Where am I? And yeah, you have 233. Remember, it's 223. We discovered that typo in the last problem. Okay. So here's P. Okay. Now let's check units of pressure. Okay. So the reference data we're given, temperatures in Kelvin, then X and Y. So Kelvin's good. So now the one thing we need to check when it comes to units of pressure, where they matter is in here. Okay, if this is in kilopascals, then our Antoine constant should return pressure in kilopascals. Okay, and so you should add comments to document this, but if I want to specify the pressure in kilopascals, well then I want to convert my vapor pressures to kilopascals so that the units up here are consistent with each other. Okay, so I just divided my vapor pressure by 1,000. Okay, and that's just so I can keep my reference pressure in kilopascals, as you had in the comments, the 101.33, and then when I plot, my pressures will be in kilopascals. Okay, so let's give this a try. Okay, I'm just going to copy and paste this. Okay, and let's run rail caller 2. Okay, so undefined function or variable T1. Oh, so I didn't go back and look at is your initial conditions. Okay, I didn't look at your initial conditions. Then I should have seen these are highlighted. Okay, so I'm going to go ahead and suppress the output here just to shorten things up. Okay, and then what I didn't see is my initial or your initial guesses. Okay, so use a molar average for. Okay, so let's. Oh, I shouldn't have deleted it. Did I delete Antoine Caller? Shoot. So I deleted Antoine Caller. So Antoine Caller, you had analytically solved for T. Okay, so if I were to go back and edit this, I might leave that so you could keep that as a means to estimate your temperature. Do you know what I mean? So if I were to, go back, I probably wouldn't have deleted Antoine Caller. I would have left it in there, so you could have, calculated this T1 and T2, which would have been my endpoints, and then use that as my estimate. Shoot! I wish I should have saved a copy so that I could come back and gotten that, but it's okay. It's not the end of the world. Okay, in the absence of that, I'm just going to steal it from my reference data. Okay, so I'm going to do T1 is equal to. So T1 would be this one, 341.85. Okay, 341.85, and T2 would be this one, 353.87. Okay, so again, I think doing this is great if you would have kept Antoine Caller and used that to estimate your two pure component saturation temperatures. Would be great. My only note if you were to do that is remember your Antoine expression uses a temperature in degrees C. And so if here we're trying to be consistent throughout and use Kelvin, you would have to take those and convert those to Kelvin, right? I make these Kelvin here because in my air function, I'm assuming this is temperature in Kelvin because it's converted to degrees C within my Antoine expression. Okay, so this is good. You could keep Antoine Caller. Again, I would just make sure when you calculate temperature from your Antoine equation, that's in degrees C, so convert it to Kelvin. Right? If you wanted to, you could also use F0 to solve for the temperature in your real law expression too, but now we're just going over the top. All right, so let me try resolving or recalculating. Bam. Okay, so that's reference data. My plotted data is way down here though. So what's going on? Okay, let me move my head out of the way and let's look through things. So my reference values. Y1 and T. P. Your estimate of Y1 is 0.5. Estimate of T is molar average of those pure component temperatures. You never collect T. Okay, so if I look at your air function, when I unpack, first element's Y, second element's T. Okay, so coming up here, you collect Y, but then T is going to be res 2. So when I plot your data, T versus X, T versus Y, right? So before, I'm guessing your temperature vector was just zeros, which is why it was a horizontal line. It was all zeros. let's see. All right. Error using horse cat. Dimensions of arrays being catenated are not consistent. Line 30. Okay, so we're getting a little further. So here. So suggesting t, x1, and y1 aren't of the same size. It's odd considering you size it using size. Oh. So what happens is here though, I need to make this sum right into the nth element, right? It's a vector. Not creating a scalar quantity. Bam! Got it. So last issue I had introduced, I just had put a t here, and so when I just had t there, then I was trying to write a scalar to a variable t, so I was just creating a new scalar variable t, which I kept overwriting, and that became my catenation issue. Was I'm transposing these three vectors and then stitching them together so they're each a column. So it looks kind of like a table. And so the catenation issues tell me, horizontal catenation means you're stitching them together this way, right? I'm creating a bunch of different column vectors that I'm stitching together. And so they're of different lengths, right? So they weren't all of the same length, so they couldn't stitch them together, right? And so, yeah, like that. That's it. Okay, so hopefully that that helps you out. So if I maximize this and just look at the big picture items, big item was that your Antoine constants, or your vapor pressure using your Antoine equation, need to be calculated from within your air function, because you're solving for t. For each x, you're going to solve for a new t. So with that t, you need to calculate the corresponding p1 sat and p2 sat, which ultimately end up in your air functions, right? The air functions are identical to the last problem. Again, the only difference is now I'm solving for y and t, so for each t, I need to call my Antoine equation to calculate the corresponding p1 sat and p2 sat. Okay, so that is the major change or feature that I have. Okay, otherwise, good job, you're on the right page. I suspect it's more of a thermo-technical detail than a MATLAB technical detail. Okay, so good job. Hopefully this helps.